reading group. As always, we will be recording, so please accept that it's okay that we do. And I will just hand it over to Sascha, who will be today presenting a paper using causal random forest estimation with an application to labor economics.
Yeah, so when I picked the paper, it was in the IZA working paper series. And you may have seen I have a certain taste for causal effects estimation and trying to learn how the new world of machine learning collaborates or not with, say, more the labor economist style causality stuff. And I think I was a bit misled by the short length of the paper, that it would be easier to prepare than it turned out to be. Also, one of the authors is a classmate of mine from undergraduate days, 25 years ago. But okay, let me just get going. There is quite a lot of equation material. I will not cover every single line for sure, and want to dwell a bit more also on the application in the end. I also asked them for the code. The code is not yet public. They are still cleaning it up to make it accessible and usable also for other applications than just one that is in this paper. So at some point, I think we can all use it for applications of our own. So this is ultimately about a way to use machine learning in the context of two-stage least squares with over-identification in the sense of there are more instruments than endogenous variables, because there is already a toolkit for the just identified case, as many instruments as endogenous variables by Susan Acey and co-authors. And this paper builds on that one and goes beyond that in some respects. So motivate a bit where this is coming from, then talk about regression trees and random forests, and then the two-stage least squares version of that. And then I'll spend, I hope, quite some time on revisiting Angrist and Evans 1998 AER. So where this is coming from is Breiman's random forests, which is by now successful and a popular method for fitting flexible regression models. So talking at the very high level, the standard kind of regressions we use in Econometrics 101 has some linear model quite often. And what we try to achieve here is to have, on the one hand, a more flexible model that maybe has better predictive power for the outcome, but also is more flexible when it comes to looking at heterogeneity by having a flexible way to get at what I might call in shortcut interaction terms. And you'll see that as we go to the application in the end. Let me just preview the application. What it's gonna be, Angrist and Evans look at the effect of number of kids on the labor supply of the moms. And the idea is that the more kids you have, the more you are busy looking after them, and that should have a negative effect on your labor supply. And what the contribution of Angrist and Evans back then was to come up with an instrument to shift the number of kids that a family might have. But they also look at heterogeneity. So they want to see whether this effect of having 3 instead of 2 kids, that is essentially what they are looking at, varies by characteristics of the father and the mother. So if a family where the father is highly educated and the mom is also highly educated, how does that effect of having this additional kid look like compared to a family where, say, the father is highly educated and the mother is medium educated, or the father is medium educated and the mother is highly educated? So it's looking into this heterogeneity where our standard regression models are relatively cumbersome, and we have to run either models with tons of interaction terms, or we run subsample analysis of some kind. But what the method that we are talking about today will give us, based on high-powered econometrics, is a way to go about this that will give us nice graphs that fit the data more nicely and give a richer picture, going well beyond the interaction terms that we would see in a standard regression model. Okay, so going back to the intro, random forest, what we start from is regression trees, where regression trees go about trying to find patterns in the data such that we can split the data into subgroups where the outcome is quite similar in a given subgroup. And I'll talk more about these regression trees in a minute, because it's never clear. Some people know this by heart, others maybe for the first time today hear about regression trees. And then going beyond the regression tree, which is one way to split the data, is the idea of bagging, to do this bootstrap trees, where you produce multiple trees. And then another variant, further sophistication, is random forest. We get to all of that. And Athi, Tipshirani, and Vaga, I assume the guy is German or Austrian, they have written a paper that extends random forest to the context of two-stage least squares, but in the just identified case. As I said, as many instruments as endogenous variables. And what these authors, Martin Bevan and Kukla, say is, well, that paper unfortunately doesn't cover the case that occurs quite often in empirical applications, namely that people have more instruments than endogenous variables. So that's what they try to get at here. So they developed the case for more instruments than endogenous variables. They provide or say are about to. So I asked them for the code, and it's not ready yet, but soon, in a few weeks' time, I guess. They also spent quite some time in the paper and also then in the empirical application on tuning issues that I also mentioned a bit further down. And then they revisit the Angrist and Evans paper that I already summarized for you a few minutes ago. So just to get you going on regression trees, here is a classical example of how a regression tree might look like. And this is using US baseball data and hitters, or people punching that ball that's thrown at them. And in this particular example, the interest is in understanding what predicts wages of hitters. Yeah? And in this particular example that we see in front of us, once the first sample split that's being done here is that people who have less than 4.5 years experience seem to on average earn less than people who have more than 4.5 years experience. Yeah? So the algorithm that's behind this sees as one first pattern, oh, we seem to have two relatively big groups. We can split our sample into two halves, or not halves, parts. They can be of different size, where one has on average lower earnings, the ones who have less experience than the ones with more experience. And then as we go into one of these branches, say the one with less than 4.5 years experience, it turns out that in this subsample, again, we may be able to split into those that have less than 3.5 years experience, and between 3.5 and 4.5, giving us two more branches. And I should also say that whenever we are at a node, that's what we call a parent, and then the next nodes below that we call children. Yeah? And in this particular case, we always have two kids for each parent. But that has nothing to do with the Angrist Evans kind of parenting kids later. That's a different thing. Okay, then the other thing that seems to be a pattern in the data is that people who have more hits, so who have been better at the game, conditional on their experience, again earn more. So we are branching off here, and it turns out that a convenient sample split in this particular data set is those that have more than 114 hits earn more than the people in this other branch to the left, where the hits are below 114. And then there is yet another sample split, and what you see always at the end of these nodes, at these terminal nodes, is the average log wages of these people. And the same happens in this right branch, where for the people who are more experienced, more than 4.5 years, we subdivide them into hits below 117.5 and so on. And all these terminal nodes then are informative about groups that in themselves are relatively homogeneous in terms of having similar wages, okay? We can then plot this graph, which only uses two variables to split stuff, years of experience and number of hits, and can display it in a different way as an area, in this case, two-dimensional, years on the x-axis, hits on the y-axis. And you can see that these same splitting rules that we saw in the tree diagram pops up here as areas in the rectangle. And it always plots the average log salary in that particular subset. And then you see points for the actual distribution of values, combinations of years of experience and hits, and the average wage or salary log wage that these people have. Okay, that is one regression tree. Here, an artificial example where you see the same kind of picture, where the square, this rectangle, is subdivided into four subsets, depending and guided by the algorithm behind it. But we might have a different tree if we randomly draw subsets of these points. The algorithm would produce either this kind of split or this kind of split. Yeah. And as soon as we go beyond to can harness the same rhythm that helps, and that's when we get into the kind of forest terminology. Now, all of this, what I described so far, would go about making predictions about one specific outcome. And the way to think about it is it's kind of OLS. Yeah, you want to predict a mean, a conditional mean. But the more general way to go about this is to say, well, what is the conditional mean? The conditional mean is also a moment condition. And as we go away from just predicting the conditional mean in a single equation, we can have more general models, say multi-equation models, or in the case of two-stage least squares, we also have two equations, as you know, reduced form in the first stage. And we can formulate that in this more general way by means of a function, the xi, of the data. And we are interested in conditional moment conditions. We want to be able to say something about this general function for specific values of x. Yeah, so we might want to say something about, oh, how is that function looking like for people with this particular set of characteristics? And then the theta is the parameter of interest that we are going after, and the nu is nuisance parameters. Yeah. And this is what we call then a generalized random forest if we use the same techniques that I described in the simple case of the one equation model, OLS style, in a more general setup such as two-stage least squares. But still, we try to split the data into subunits where we try to maximize predictive power. Okay, now, if we are in the case that we are working towards, which is having more instruments than endogenous variables, then there may not necessarily be an exact solution, but we try to minimize this function on the right-hand side. And what this is that we use local weights, and all of this is similar to trying to smooth a function. So what are these weights here? The weights try to give weight to points as neighbors in the following way. L is the set of observations falling into the same leaf, so into the same part of the tree, as the test point. Yeah, so let me just jump here. That's again the kind of artificial example we saw 1 or 2 slides ago, where we've highlighted one point X. That is our reference point for the formula that I'm not talking about. So we may, as we build different trees, try to find weights that tell us how often another point somewhere in the neighborhood falls into the same box as our point of interest. Yeah? And that way we know how relevant that point is in terms of helping us in the prediction in our function of interest here. And here is an example where the different colors here, or the different kinds of dots, the small black dots and the hollow larger ones, try to characterize that this set of points has a different weight than this set of points. Why? Because this set of points more often falls into the same rectangle together with our point of reference X than this set of points further away. Now, there are lots of terms here that we could spend ages on explaining in detail. On a few slides, I will go a little bit faster maybe. So AC and co-authors in their paper last year that is published, they talk about the successive splits that we do in the tree, and that one element in the algorithm is that we compute a pseudo outcome, rho I. And what you can recognize here, and we can't go through every single element of these formulas, I just want to highlight a few things. This nabla here always tells us about the derivative, yeah, directional derivatives of this multidimensional function we are talking about, namely this one here. And this pseudo outcome plays a role for us to know how exactly to split as we go from one parent into the children, into the different branches. Okay. Now, what is common to a lot of these machine learning methods is that we might split the sample into 2 parts where we do different things. Either that comes in the form of a training sample, and then we use whatever is done in the training sample to make out of sample predictions in the non-training part of the data set. And here, the same idea, the same, say, high-level idea is used in what they call an honest subsample splitting technique, where we use one part of the data to grow the trees, and then use the other part of the data to solve the main estimating equation. This is stuck. Why is it stuck? Okay. Then obviously there is also variance estimation involved. We don't just go after point estimates, and again, an unpleasant set of formulas that get richer and richer, if anything. Why does it not go forward as I like? Okay. So moving towards the IV case. So far, I've been talking about a general objective function, but now we bring the case of 2-stage least squares to give meaning to this objective function. So you see the same function psi, but now on the right-hand side, we have things that may be more familiar from instrumental variance estimation. Namely, we start from a structural model where there is an outcome, and then we have a treatment, W, and we have a coefficient. And you notice here the coefficient is not just tau, but it's tau of x. Yeah. So what is built in already is heterogeneity that we will be interested in later on. Namely, we want to see whether the effect of the treatment on the outcome varies along the distribution of the covariates. So in the context of the kids and labor supply, whether different characteristics of the parents interact in certain ways with the number of kids to determine the labor supply of the mother. So what we have in this case is that the W may not necessarily be orthogonal on the epsilon. So we have an endogeneity issue, which is why we use an instrument. And that later on will be the same sex instrument. If you have 2 boys or 2 girls as the first 2 kids, you're more likely to want a 3rd kid in order to have sexes at home. So what is this first equation here? The first equation characterizes the exclusion restriction, yeah, that the Z, the instrument, should be orthogonal on the epsilon hat. And the second equation is the moment condition for the intercept. Now that is all in Athey and co-authors last year, but their case is one that can only deal with the one instrument case, or in a more general case, as many instruments as endogenous variables, but not with a case where there are more instruments than endogenous variables. And that's where now the Bevan-Kukla extension comes in. So if you have more than one IV, but still one endogenous variable, so the over-identified case, then you have to do what is described in Wooldridge in the panel book, not the introductory metrics book. And that is that you stack equations. You bring together the first order conditions of the first and second stages and stack them. I had an email exchange with Martin Bevan yesterday because there seem to be 2 different editions from the same year of the same book in different countries. So my Wooldridge has this on page whatever 187 and his Wooldridge on page 529, and we couldn't figure out why, but that's what it is. And I have both editions now if you ever want to look it up. I have scans of both. Okay, so this is the stacking that now allows us to have a even more general psi function for the over-identified case, where this is the implementation of the psi in our case. Now, this always goes back. It's really strange. Sorry, I need to use a different button. Okay, then I'll skip over these things. They are getting too complicated, too detailed. This is just deriving how to come up with a solution for this system here. And I just left these formulas here for you to appreciate that this is not trivial stuff. That shows you the partial derivatives of this conditional expectation function. So let's spend some more time on this slide then, maybe. Tuning. So I don't know how much you know about machine learning, but in machine learning, you always have a lot of choices to make. My personal parallel I draw from my younger days is propensity score matching, where also you have loads of choices that are a bit of a black box, and in the end you show some nice results, some nice table, but in the background you have been cooking up like an alchemist in the Middle Ages, all kinds of choices that are hidden. Machine learning, we have that. In the case of random forests, we have issues such as defining a minimal node size. So as we go and build a tree, we want to avoid nodes that are maybe a single observation. We may say, oh, we want at least 5 observations in every node. Otherwise, a splitting is not allowed to happen. Then the subsample fraction, how large should a branch be, or a child branch be, relative to the parent branch? Also, the number of variables that we use for splitting. Yeah, in the hitters example earlier on, we just had experience and the number of hits in your career, 2 variables. And that's another choice we have to make, how many variables are involved in our splitting. And then there are parameters to control the imbalance of the split. We have one parent say, we split it. The split is not necessarily 50-50. It could be 80-20, but maybe we don't want 199. Yeah, so again, that is a parameter that is being tuned. And the optimal choice of all these tuning parameters is an open research question. So Chernousukov-Hansen, in the context of IV, argued that what we can use to inform the choice also of tuning parameters is that we use the reduced form, okay? And the loss function they propose in the IV context is this one, where you can recognize certain elements. That's the outcome. That's the predicted outcome where xi, or where I have taken out the observation itself, the one of interest. And that's the loss function we go about. Click the other one, this one. Okay, so this is what I want to say about the econometrics behind this before moving to the application, which then tells us where this method is giving us advantages over the previous work of Angrist and Evans. Okay, so what is the Angrist and Evans application? They use US census data from 1980, have 250,000 observations, married women aged 21 to 35 who had at least 2 children. Yeah, so it's a very specific sample. And I remember we discussed this particular paper during my PhD. And at the time, all this stuff about local average treatment effects and so on was still relatively new. And there was then always a critique, okay, fine, this paper may be cool in terms of having an instrument that's convincing, but it is a very specific sample, yeah? So if you set out to say something about how does female labor supply react to the number of kids, then writing a paper only comparing 3 or more kids to 2, exactly 2, is a very specific application, right? Because we're not speaking to 0 to 1 kids, 1 to 2 kids, or 4 to 5 or 5 to 6 kids. We literally just speak about the decision or not to go beyond 2 kids if you have to, yeah? So what's the outcome in this paper? It's the yearly labor supply measured by a dummy, which is worked for pay, so worked at all. And then the continuous outcome is weeks worked. And the treatment is whether a woman had more than 2 kids as opposed to exactly 2 kids. So again, we throw out all families that have 1 kid or 0 kids. What are other covariates that go in, and that also then will play a role in the heterogeneity analysis? It's race, it's mother's education in years, her age at first birth, father's income, and whether the first child was a boy. And the IV strategy is the so-called same-sex instrument that in labor economics is quite well known as an IV. Now, why do we have an endogeneity problem at all? Well, because people who have certain preferences for work, if you are, say, a McKinsey consultant and you just love working 18 hours a day, then maybe having kids is not your thing because you are just a workaholic. so that the number of kids is a choice. So we need to find variation, the number of kids that's independent of the preferences or abilities that determine labor supply. And this is where sibling composition comes in as an instrument, where the empirical regularity is that if the first two kids are of the same sex, then the parents are more likely to have a third kid. So it seems to be an empirical regularity. Whatever goes on in people's head, I don't know, but we observe that families that originally have two girls or two boys are more likely to have a third child than families that have a boy and a girl or a girl and a boy as the first two. Now, a single instrument version in this case is to say, define a dummy variable for whether the first two kids are of the same gender. The two instrument version is to say, well, we have either two boys or two girls. So that's two instruments that can be 0 or 1. So deliberately, Bevan and Kugler pick this richer case. I should say Angrist and Evans do both. They do the single instrument case in their AER paper, 1998, and the two instrument case. But Bevan and Kugler jump on this two instrument case in order to have an application that goes beyond the AC et al. Case. Now, what Angrist and Evans do is they show some basic heterogeneity, and I'll talk about that in a few minutes, where essentially they interact the treatment with characteristics of either the father or the mother in order to see whether the treatment effect varies in these covariates of mother or father. And this is also where Bevan and Kugler go beyond that by using the two-stage least squares random forest to get nice pictures, they are beautiful, and give you a much richer picture that shows you how along several covariates, the treatment effect co-varies as we change the mix between these covariates. Okay. So some words about tuning. I try to explain a little bit what parameters of interest are. And I mentioned minimal node size, the subsample fraction, the number of splitting variables. Then there is a balance parameter alpha, and there is the imbalance penalty. So whether the two children nodes to a parent are 199 or 595 or 50-50. And that's just the definitions for two of these tuning parameters in words in example 1 and 2. Anyways, what they show in the paper is these pictures here. And what are they? They are based on kriging. And kriging, what is kriging? It's a kind of smoothing of spaces. Yeah. And the way you have to think about these tuning parameters, you have several tuning parameters, and you have a loss function. And there we go back to what we talked about earlier, the pseudo outcomes. So you try to find a mix of these values such that the loss function is minimized. And that is a multidimensional smoothing issue. What we see here is the one-dimensional version of that, where on the y-axis, we have the value loss function. And what the different colors of the curves tries to symbolize is 4 different iterations, 4 different versions of the kriging procedure, where in all cases, and that's what the graphs are meant to show, independent of how exactly the tuning parameters are set and whether we do subsequent different draws of the data to do the same kriging procedure, we always tend to end up with the same minimum, and also in other parts of the distribution, the different iterations are not too far off from each other. In other words, the whole procedure is not super sensitive to the particular mix of tuning parameters chosen. Yeah, maybe not surprising given the 250,000 observations, so big data for labor economics when we talk about the 1990s. but it's just meant to instill a certain degree of confidence that this is not too sensitive towards the particular mix of tuning parameters. Yeah. So in the same way that my matching analogy from 20 years ago, one would want to show that different matching algorithms give you similar results, so that it's not too sensitive to how exactly you pick your control units. So they show the same for the two outcome varies. The first graph is about whether someone works at all. This one relates to the continuous outcome, weeks worked. And then here you see the loss function values, and they are the ones that we can read in these graphs. So here you see the 0.23 something, and in the next graph you see the 435. And at this value of the loss function, the following combination of tuning parameters is corresponding to this particular minimum loss value. The minimum node size of 1066 in the case of worked for pay, and 6 or 1 is the minimal node size for weeks worked. Okay, so that's the underlying tuning parameters that they spent quite some time on. For some reason, always the slide jumps back at me, and I don't know why.
So can I ask a question?
Yes.
I was wondering, what do you think are the necessary conditions for this method to be useful? So an obvious one is having a really large data set and many covariates.
They don't, my impression is it is quite data hungry, but they don't really speak about that at all.
And also I was interested that
I can only speak intuitively. My hunch is it is data hungry, but there is no discussion about that in that paper. Yeah.
And was there anything about using continuous or versus like categorical instruments?
No, because they are in the business of really trying to replicate this particular paper.
But I was just wondering if they selected the paper because it was like useful for the method.
I think so, that there was this kind of reverse engineering. Yeah, they had this application in mind, and they felt that there is an extension to be written about the AC et al. Method for the multiple instrument case. And typically the binary instrument case is the simplest to deal with. But again, the paper being so short, it doesn't talk much about the kind of genesis of what made them look at this and make these particular choices. But I'm happy to ask them that. I've been corresponding with them over the past days to check on certain things, and they're curious also to hear feedback like this. Yeah.
Yeah. The reason I ask is sorry, the reason I ask is it can be really useful to put these kind of methods in pre-analysis plans, because then there might be situations where you don't get access to the administrative data until a later date, and you kind of like, if you put it in your pre-analysis plan and it turns out to be useless because the data was too small, or there's some feature that the data can't, just not sufficient for the method, then it might not be as useful. So I think like knowing what are the kind of where it really outperforms just like specifying subgroups would be like really valuable to know.
Yeah, I don't think I can speak to that, to be honest, but I'm happy to ask them and report back. Yeah. Okay, that's the graphs that the paper puts out that shows us things as follows. So on these two axes, we have mother's schooling and father's income. They take this particular mix, and then you see this nice mountainous shape that displays the associated treatment effect of having more than 2 kids on the outcome of interest, in this case worked for pay, And what you see is that the treatment effect is most negative in a kind of middle range of father's income and in the middle range of mother's schooling. Okay. But we can also see that there is by no means it's a monotonic relationship. There are these different valleys and hillsides. So it gives us a much richer picture than what we would have taken away from the original Angrist and Evans paper, which I'll demonstrate to you now. So in Angrist and Evans, they do interaction terms not for combinations of variables as these graphs do, where we have father's income and mother's schooling interacted, but in the Angrist-Evans paper, the only interaction terms between the treatment effect and one of these variables, say father's income, and then separately, say the treatment effect for along the dimension of mother's schooling, but not the two combined. So here is the numbers that we are talking about, and they come from this particular table, which is table 9 in Angrist and Evans. And here you see in the final column the two-stage least squares estimate, where we see the bottom third of husband's earnings distribution is associated with a treatment effect of minus 1.22. And that is the number that they report verbally in the text without displaying the table. And then for father's income in the middle third of the income distribution, the treatment effect is strongest. That's also what we saw in these pictures. And then for father's income in the higher third, it's a smaller treatment effect than in these other two terciles. And all of that are numbers that come one-to-one from the Angrist and Evans table, and that we see reproduced in this graph. So ignore the mother schooling dimension, just read like the outer envelope of this picture. And we see exactly that, namely that the treatment effect is most strongly negative in the middle. It is less negative in the lower third of the income distribution, but it's even less negative as we are in the upper third of the income distribution. So high income families, high father's earnings families see less of a labor supply hit for the mom when a third or fourth kid is born. Okay, so summarizing the picture in relation to what Evans and Angrist gave us, the results appear somewhere in the graph. So these average effects in bitercile, we also can see in the picture, but the picture is far richer and on top allows us to study combinations of several variables and see them with our own eyes.
Sascha,
okay. What we haven't talked about.
Yeah, can I ask just a short question? It looks as if you really need lots of power here to fill in all these cells. So I was wondering if they also, I guess they do, they show some sort of standard errors around this.
Yes, exactly. That is the standard errors. Okay. So that's a plot that has the same variables on the axes, but now what we read on the axes is the standard error. And you see the standard error is lower in the middle range or in the combination of these two variables in the middle tercile of income, but it's pretty high at the extreme. So for very low income fathers, the standard errors are particularly high. So if you think about the associated treatment effect, which here is anyways only little of 0 in this corner. You see my mouse when I do this?
Yeah, we do,
And in that corner, also the standard error is particularly high. So arguably, we can't say anything of a negative, statistically significant negative effect in that corner, but in the middle range, yes.
And is this a function of the observations you had? Maybe
yes, absolutely.
Yeah,
absolutely. Yeah, it depends on how dense the data is in different ranges, value ranges. Yeah. Okay, then this is the equivalent curve for weeks worked, and again, all we take away is this picture is richer than what we would get by just looking at the table in Angrist and Evans, which is 3 numbers. Yeah, we have hundreds or thousands of numbers in this graph, and it gives us a richer picture of how the different characteristics of mother and father interact to produce a certain treatment effect. Yeah, that's the beauty of this method, I would say. Yeah, and if I again draw my crazy parallel with matching, a method that never really took off big time, to be honest, is generalized propensity score matching, which also tries to produce nice pictures, having continuous treatments where you use matching to predict different values of the treatment that's continuous, and then plot a dose response function. Yeah, that's my high level comparison to the matching world. So these pictures are beautiful on the one hand, but if you are the kind of reader that says, okay, what's the one headline figure I should take away? Well, yeah, that's not what it's made for. Okay. Okay. Here more interaction effects. That's again worked for pay, and now it's mother's education and mother's age. So you can bring together whatever covariates you want to combine and study how age and schooling interact. And then this is a graph I quite like. So they say that they copied or learned this way to present heterogeneity of all of these different pictures in one big graph, but again from Athey and co-authors, but a different paper from 2020, which is mimeograph. So I couldn't download it. It's nowhere to be found. But what this tries to do is to say, okay, let's look at deciles of the treatment effect. Yeah. At the first decile, the treatment effect is particularly negative. At the highest decile, it's essentially 0. Yeah. And that's how the treatment effect looks like across the percentiles. And then what these curves show you is which groups or which covariates are represented or behind particular values along the percentile range. So what you see, for instance, is that if we look at people who are Black or Hispanic, so minorities, that's the 2 greenish curves. There we have a particularly high representation at this particularly negative treatment effects. Yeah, you follow me? And if we look at high social status families, or not high nonsense, forget it. Erase what I said, nothing about status. But white mothers are more likely to represent it at the upper end, where the treatment effect is relatively small, close to 0. Yeah, Gaurav.
Yeah.
Go ahead, Gaurav.
No, I just had these deciles are the deciles of the treatment effect itself, or deciles of income?
Of the treatment effect
itself. All right. Okay.
Yeah. Yeah.
Sorry. Yeah.
Because it's a model that models heterogeneity of the treatment effect. Yeah. Which is why we had tau of xi times treatment. And now we say, okay, this tau we can split into percentiles, deciles, and then ask ourselves, what are the typical characteristics of families that are in the first decile, second decile, and so on, 10th decile? And it turns out that the Blacks and Hispanics are stronger in the first decile, which is the one with the most negative treatment effect. So where the additional kit gives you the biggest hit on female labor supply, on mother's labor supply. So I think it's a pretty nice way to present results. And maybe that is the takeaway message you would also give to policymakers and say, okay, look, the world isn't that easy. It's not just one number, but as a policymaker, you should be interested in heterogeneity for different subgroups. And here it is in one chart. Okay.
Sascha, on the bottom
yes,
graph,
Matthew.
the treatment effect graph, could they put confidence intervals over those? Or would it be difficult to do that?
No, I think they could. Yeah, they could. Yeah. No reason.
Because I mean, if it like say
why they don't, I don't know, but yeah.
Because if even there could be a situation, even though the treatment effect is large, you could like maybe the confidence intervals like blow up there. It might not be the case, but and then it's not as useful, I guess, to.
Yeah, you're right. Okay. Then similar graph for weeks worked, where again the treatment effect varies somewhere between 0 and -12 weeks. And again, we can study what are the covariates underlying the treatment effect in specific deciles.
Sascha, just to, I mean, this picture looks really interesting, the summary picture. Just to clarify, if you could put up one of them. So supposing I look at this top line, you know, the yellow line at the top. So how, what, could you just clarify what exactly is it measuring? It's measuring the number close to 0.9, let's say. What is that measuring?
Yeah, for binary variables, it's slightly more tricky. Let's do father's income. That's easier to interpret. So at the highest deciles and percentiles of father's income, the treatment effect in terms of mother's labor supply is less negative. Yeah. So at this, the blue curve is pretty much monotonic, going from that father's income, families with higher father's income are more likely to see a relatively small labor supply effect for the mother in case of third or fourth child beyond the second. Okay, I have to come to an end. So what this paper does is it generalizes a paper by Athey and others last year that tries to bring random forests to two-stage least squares estimation. And while Athey and co-authors only covered the single instrument case, or the just identified case, this paper goes beyond that. And it also spends a bit more time than the Athey et al. Paper on describing tuning parameters and how those should be chosen and how to go about estimating them. And ultimately, they hope in the next few days or weeks to upload their code on GitHub and then hope that more people apply this. As we all know, unless there is code, the applied community typically doesn't make much of fancy econometrics papers. Now, finally, a bonus slide that I found this morning on Twitter, but relates to the topic. I don't know whether you've seen that, which is about car seats as contraception. So that paper shows that as US states introduced compulsory car seats for kids, those states that introduced them earlier not only saved kids' lives, which is the intention of having car seats, but also had some collateral effect, which is that in these states, fewer kids were born. And the logic is, I do have 3 kids, so I know what they're talking about. As we had the third, not all 3 car seats would fit in our 5-seat car. So we had to buy a 7-seat car as we had the third. And we, at that point, were happy to do so, but many families are not. So as they knew, oh, if we were to have a third child, we would need a third car seat. Some people don't have a kid, as opposed to buying a bigger car. And it turns out that while car seats only saved 57 lives, the bigger effect they had is that overall in the US in the last decades, there were 145,000 fewer births as a result of car seats, compulsory car seats.
That's a super cool paper. Thanks for flagging that.
I love the title.
And I mean,
okay, guys.
I think of Arthur, who's just had twins.
Sascha,
Yeah.
can I ask a question? So
you can.
Then in the two instrument case, initially I thought, whether they do they speak about situations where the instruments are correlated versus not, and that brought me to thinking about the two instruments that are here. Are they? I mean, you can either have two boys or two girls. So. And that's a very specific situation in the multiple instrument case.
Yeah, agreed.
And so I'm not sure whether, is this something that's, they mention and that they are, that's important for their method, or?
No, and that's also something I need to get back to them about, because as you say, when the instruments are too correlated, that brings in weak instrument issues, at least. And I'm not sure how robust this method is to that complication. Okay. So as you say, this particular two instrument case is a very specific one. Yeah, and I haven't given much thought to how it would affect the estimation. Yeah.
And the other thing is with, the two boys and two girls thing, I'm not sure whether that's like completely random, especially when it then comes to the interaction with certain family characteristics. One could still think that, there's a push from the father that, you have two girls, but you need a male heir for the little kingdom kind of thing. That drives the treatment effect differently, and then you could, you control for some family characteristics, but I don't know how it pans out with the interaction terms. And if those interaction terms then,
fully agreed. What's the idea of even playing with the two instrument case in this application? Well, because you suspect that the treatment effect may be different, or that the two instruments, the two boys, the two girls, have differential first stages. Yeah.
Sascha, one quick question. When you look,
Klaus can now correct whatever I said.
No. I was just thinking regarding the hyperparameter tuning results. So the first moment I saw them, I was like, whew, those are weird parameters that got chosen. So those are usually not the ones. Like,
you mean the node size or what?
Yeah, exactly.
Yeah.
Also, the loss was quite different between the two tables or something. Yeah. And so the thing is here. Okay, so are we trying to predict something here, or are we trying to fit a function? Because the way it's set up, it doesn't seem to me that we're using machine learning to predict something. We're more trying to fit a function as good as possible.
Yeah.
And in that sense, this would not be just restricted to random forest, because I don't think we care about prediction here, or do we care about finding the best approximation function? That's what I'm not fully clear.
Yeah, no, I think it's mainly the paper works towards these nice pictures, so trying to display heterogeneity of the treatment effects. Yeah, it's not about prediction per se in terms of the outcome.
Yes,
but ultimately, of course, we do predict the outcome.
No, but the way it seems to be set up is kind of violating some kind of train test split paradigm, because the way we fit is like we're trying to on purposefully totally overfit the data.
So you say you would never choose node size as the tuning?
No, right? No, that's the thing. But if that's what the node size they got, that seems to be like, okay, that's a very odd choice usually.
Yeah.
I think, or personally, I mean, I don't know what they do. I just recall a bit the essay and Varga paper, and I think this dishonesty condition kind of goes like, or that's why they do it, right? To like basically determine all the leaves and all the nodes and stuff and node size in like one part of the data, and then basically predict the outcome or estimate the actual treatment effect or the objective function, main objective function in a completely separate data set, so that you kind of, right, that you don't have this issue that, right, you use part of the data once again to like estimate your objective function. So I think you do all the classic machine learning stuff, right, like training sample validation and stuff like that in one part of the data, and then you really have this unseen part where you then use to like get the minimum for your objective. So I guess this, I mean, I'm not an expert by any means, but I think that's like why they do this kind of like why. I think they developed it earlier in a 2016 paper, like in
sample splitting,
right? Like the dishonesty kind of condition.
But the node size, they're estimating the treatment effect within a leaf, so they need like lots of observations within a leaf to be able to estimate a treatment effect within a leaf. So if you have too few observations, there's like not much you can say within that leaf. So that might be why that leaf size is so large.
But it's multiple trees. That's what's, like it's not just. So
you have to, like the tree has to terminate somewhere, and one of the rules is the node size can only be this.
No, they prune the tree on purpose. That's usually what you do. You have very shallow trees, and then you have like thousands of them.
Yeah.
Here it seems to be the opposite case. A few trees with a lot of.
No, they'll still be estimating thousands of trees, for sure. Like, I mean, I don't know. I don't know if I overlooked something, but I think that there will be, and if I remember correctly, they like they use parts of the data each time.
Okay.
They hold out random parts of the data each time.
Yes, I think they still do the classic, right? That they estimate, I don't know, 1,000 different regression trees, right? To like, and then do the average kind of thing. But yes, I mean, when I read it, I was also kind of puzzled that you have like such like a deep tree with like 1,000 nodes. That's just like really uncommon, because it, like, right, usually you truncate your trees at some point. I mean, apparently it's the best fit, but maybe it's because the data is so big. But for machine learning cases, it's not even that big with 250,000. So yes, it's a bit puzzling.
No, but thanks, Sascha. Thanks very much for the talk. This was amazing.
Yes, thanks so much, Sascha. That was
thank you.
It's great, especially that the paper is not that easy when you read it the first time to like think about how to frame it in an understandable way. It was great. Oh.
Okay, guys.
Yeah.
Good to see you. See you next time.
And I just want to say thank you for, not